Okay, this is example program unit C3, page 4. Let's take a look at the program. Okay, it looks like this is a tank. Circular cross section, 1 meter diameter, so like this big, okay? So, let's take a look. A stream of water, diameter D is 0.1 meter, which is very, very small diameter. This is flowing out of this tank, okay? Steadily, so this is a steady state flow, okay? The tank itself has a diameter of 1 meter. Let's determine the flow rate Q needed from the inflow pipe if the water depth is to be maintained constant, which is 2 meters. Okay? So let's move on. This is the picture I copied from the problem statement. So it looks like this is a circular cross-section diameter tank. 1 meter, which is not so big, okay? Depth is 2 meters. Alright. So what kind of thing is this? This is probably the water heater, okay? And this is outgoing flow. Diameter of the outgoing flow is 0.1 meter. Okay. Now obviously, in order to maintain this constant depth of water 2 meters, whatever the volume of water coming out need to be resupplied from the incoming flow, which is flow escaping from this tank is exactly equal to the flow incoming. So let's express that using flow rate Q. Flow rate Q is the cross-section area multiplied by velocity. So let's call this Q out. This is Q in. In order to maintain the constant depth H, of course you have to have Q in is equal to Q out, which is equal to Q. Flow rate need to be constant. This is called continuity, but anyways. So I'm going to, first of all, let's define the streamline, because I want to solve this problem using Bernoulli's equation. So this is the streamline I'm going to define. Okay? Then I'm going to define location 1 right here. Okay? So location 1 comes with velocity v1. Cross-section here is, of course, pi over 4 times diameter d, 1 meter squared. That's the cross-section 1. Let's define the location 2. Right here, this is outgoing flow. Velocity is v2. So obviously, cross-section area here is pi over 4 times d, lowercase d, 0.1 meter squared. So whatever the cross-section area here multiplied by velocity v1 gets you Q, flow rate, incoming. Velocity times cross-section area here gets you the flow rate outgoing. Happen to be flow rate in and out must be the same in order to maintain 2 meter depth constant. This is obviously steady state problem, okay? That's why you can apply Bernoulli's equation along a chosen streamline. Okay? Okay. So let me solve this problem. First of all, let's apply Bernoulli's equation. Between point 1 to point 2. Okay? So this gives you P1 plus 1/2 rho B1 squared plus M1 must be equal to P2 plus 1/2 rho B2 square plus gamma Z2. This is Bernoulli's equation. Let's take a look at each term one by one. Pressure at point 1 P1. This is the surface of the water, called free surface. At the free surface, pressure is local atmospheric pressure. In other words, this is a zero gauge. So zero gauge, free surface. Zero gauge. How about pressure at point 2? This is obviously free jet, okay? Free jet, again, zero gauge. So both 0 and 0, okay? So what else do we know? Well, let's measure the elevation or height Z. Let's measure height from Z. Upward positive. If I measure Z from here, of course Z2 is 0. Z1 becomes 2 meters, right? Okay. So this is the equation coming from Bernoulli's equation. You have two unknowns. What are those two unknowns? Velocity v1 here, we don't know. Velocity v2 here, we don't know. You have two unknowns out of this single equation. Whoops, you can't solve this problem, you need another equation. Okay? So what I'm going to do is I'm going to apply continuity. This is continuity, by the way. So continuity equation basically says that flow rate in is equal to flow rate out, Q1 is equal to Q2. In order to maintain constant depths, yeah, of course. So flow rate is cross-section area times velocity. So this is going to be pi over 4 capital D squared times V1. This is pi over 4 lowercase d squared. V2, pi over 4 cancels. So this is going to give you the relationship between velocity v1, v2. v1 is equal to d over d squared times v2. So let's call this equation 2, this is equation 1. Can we combine equation 1 and 2? Yes, we can. So let's combine it. If you combine equation 1 and 2, you are going to end up having this kind of equation. V2 is equal to square root 2 times g times h divided by 1 minus d over d to the power of force. This is the equation you're going to get by combining equation 1 and 2. Make sure you do that. Do it yourself. Make sure you can get this equation out of those two equations. Okay? Because if this is exam problem, I would expect you to get this one by yourself. If you can't do it, you can't solve this problem. So please go ahead and do it by yourself. Okay? So anyways, if you plug in the values for this equation, it's going to be square root of 2 times 9.8 meters per second squared. This is the standard gravity at sea level. Let's assume that h is of course 2 meters. We want to maintain constant. 1 minus diameter ratio is 0.1 meter over 1 meter to the power of force. V2 is 6.26 meter per second. Good. So once you get the velocity V2, of course you can define flow rate by either B1A1 or B2A2 because it's the same thing. So once you know B2, since you know B2, let's use A to B2 to find out. So Q2 is equal to Q1 equal to Q, which is equal to A2 B2 or A1 B1, either one is fine, but let's use A2 B2. So pi over 4 times 0.1 meter to the square times 6.26 meter per second. Flow rate, you can determine 0.0492 cubic meter per second. All right. Now, this is not end. This is the solution. I keep solving this problem by assuming that, hey, this is not so large tank. This is not the large tank as it looks. 1 meter diameter, 2 meter depth. No one really calls this as a large tank. Okay? So let's just consider, can we still solve this problem assuming this is a large enough tank so that flow behaves like a large tank? Okay? So I'm going to draw a picture here. Same picture, okay? What if we assume this? Large tank. Which is in this case probably not. But let's do it anyways. See what happens. So this is the same situation. Not so large tank, but I'm going to assume this is a large enough tank. Okay. So water is incoming. And water is outgoing. Okay. You're going to maintain the constant depths, 2 meters. All right. If this is a large tank, what happens? Let me just draw a streamline for large tank. If this is a large tank, incoming stream hits the surface here, then lose the velocity. So probably just wander around and slowly picking up the speed and then suck the end and flow out. So this is a typical large tank behavior. Okay? So let's go back and take a look at the original picture here. So original program statement says this is a 0.1. Wait a minute, 0.1's here? 0.1 here means that velocity at 0.1 is probably 0 approximately, because water gets in, hit the surface and lose the velocity, and then gradually, slowly picking up the speed and sucked in and flow away. That's typically how large tank behaves. If this is a huge tank, it behaves like this. Okay? So if so, this location is location 1. B1 is approximately 0. This is large tank assumption. Okay? Now let's go back to this original solution of mine. Now this solution, I didn't assume that way. This is not so large tank. If the tank is not so large, what happens? When the incoming flow hits the surface, immediately pick up the speed and flow away. If the tank is not so large, that's what happens. It acts like a pipe flow. Is that right? If the tank is large, right here on the free surface, you're going to lose the velocity once, and then slowly picking up the speed and then flow away. So if I try to solve the problem with large tank assumption, what is the difference from that solution? Okay. Now, large tank assumption really means that we're not going to use continuity. large tank assumption is a violation, essentially. Violation of continuity. Okay. We're not going to apply continuity equation. Why this is violation? Large tank really means that cross-section area A1 is approximately infinity. That's why B1 is approximately 0. That's the meaning of large tank. So that means right here, continuity cannot be applied. Okay? So, let's do that. So this is location 1, this is location 2. So let's apply Bernoulli as it was. So Bernoulli says, same equation. P1 plus 1 half rho B1 square plus gamma Z1 is equal to P2 plus 1 half rho B2 square plus gamma Z2. Now, this is a zero gauge, free surface, free jet. B1 is approximately 0, large tank. B2 is unknown, Z2 is 0, this is H, which is 2 meters. Okay? So, what happens to the Bernoulli's equation? You can actually determine B2. What is B2? B2 is equal to square root of 2 times gamma divided by rho times Z1. Okay, gamma over rho is square root 2 times GH, Z1. Z1 is H. 2GH. Okay? Wait a minute. What is this equation? Equation of free jet. Remember? Free jet velocity right here at location 2. Suppose you have a tank of depth H of water. You open up the hole on the bottom. Velocity gets out. It's a free jet velocity, which is equal to square root 2g of H. H is the depth. Okay? So that's exactly what you're seeing here. So the velocity here, B2, is a free jet velocity. That's this, okay? So free jet velocity, if you plug in square root 2gh, it's different from here. Okay? So B2, if I do not assume large tank, B2 is not the free jet velocity. But if I assume large tank, B2 becomes free jet velocity. Okay? So flow rate, let's call this Q0. This is the flow rate with assumption of large tank. Q0 is B2A2. B2 is this. So this is a square root 2gh. H is 2 meter, g is 9.8 meter per second square, times pi over 4 times d squared. Okay? So obviously quite a bit of different equation here. So in this solution, B2 is this. B2 times A2 gets you this much flow rate. Large tank assumption, solution is much more simpler. B2 is simply free jet velocity multiplied by cross-section area gets you flow rate. Okay? So let's go back all the way. Let's go back all the way to here. Let's try to zoom in a little bit. Let's take a look at a little bit more details. Okay? All right. So this is the plot. Q over Q0. Q is the flow rate based on the first solution, which I don't assume this is a large tank. Q0 is the flow rate solution by the assumption of large tank. If you take a ratio, Q over Q0. Okay? And this is a ratio of the diameter of outgoing flow to this diameter. Okay, let's go back here. Okay. So, in this example problem, lowercase d is 0.1 meter, diameter d is 1 meter. So, if you take a ratio d over d, it's 0.1, so it's here. So, if you take a ratio q over q0, it's about the same thing. So, in this particular situation, if the tank diameter is 1 meter, outgoing flow is 0.1 meter, you can solve this problem either assuming not so large tank or assuming large tank. It's about the same result coming up. But suppose, okay, if this diameter d is 0.5 meter instead, I can easily erase out this 0.1, put the 0.5 here to make a midterm exam problem. What happens if I do that? All of a sudden, the ratio becomes 0.5, right? Whoa! You are going to introduce a difference between flow rate. So this essentially tells you how much percent error you are going to introduce by assuming large tank. You're going to introduce about 2.5% error by assuming large tank, if this is 0.5 meter diameter. So that means if you draw more water out, you need to keep more water in, then this tank is not going to act like large tank anymore. Right after you add the water, immediately you are going to pick up the velocity and flow away. This whole thing acts like a pipe. But as long as you're talking about 1 meter diameter and 0.1 meter, small tiny water is taken out, so you only need to add small tiny water. If so, once the water hits the surface, it just loses the velocity, stagnate a little bit, and then slowly pick up and flow out. That is the behavior of large tank. So this tank can act like a large tank. It depends on the ratio. Okay? That's what you see here. By the way, this is a handout. Let me show you the handout. So this is a handout 6, which is essentially the same thing what I showed you as an example. So this is a problem, same exact problem, solved by solution without large tank assumption first, and then compared against solution with large tank assumption. Then you take a ratio, then find out the equation, then plot that equation for ratio to the ratio of the diameter little d over capital D. Okay? So please take a look at this handout. This is quite important. And let's stop here.